Good afternoon, everyone. Thanks for coming. My name is Xue Zhang, and I'm a software engineer from Cloudera, and I'm a Hive PMC as well as a committer for Apache Peak project. Here are my partner Ray from Intel as a software engineer too, and he's a Hive committer. So today we are presenting you Hive now Sparks, which means that Hive queries can now be executed by a new execution engine, Spark. So as we all know that Hive today, your query is actually get executed by either MapReduce or Tez. So Spark is the new newcomer for to support your Hive queries. So here is the outline of my talk. So I will give you a little bit background about why we are doing this and what are the benefits of for doing so, and followed by architecture overview and some design details if you are interested. And also, I like to share with you about the challenges that we have faced and provide you some updates up to date. And then my partner Ray will share with you about the benchmark we have done, and followed by a joint Q&A session. So background. So as you all know that Apache Hive is very popular in the Hadoop world about the data analytics. So because of the familiar SQL interface, and so it's very popular because the SQL-based data processing tool, and it has a large user base. In fact, in Cloudera, we have 95% of customers using Apache Hive. So at the same time, you also know that Hive Spark has gained a significant momentum in the past few years as a generalized data processing engine, which is positioned to succeed MapReduce framework. So therefore, because of the two popular projects, marrying the two, which means that integrate the two will provide benefits for both communities. So therefore, we created a Hive 7292 to track the progress on Hive on Spark project. Here is the motivation why we are doing so, and of course, it's our vision that Spark will succeed MapReduce. And because today Hive's majority Hive queries is still executed by MapReduce, so we like to provide you alternative. And also for existing Hive users or for future Hive users, replacing MapReduce with Spark as the execution engine provides better performance and better user experience. So with this goals to be achieved, we expect that there would be greater adoption in both communities. So since the inception of the project, we have gained significant momentum in both communities, in Hive and Spark, and also we got contributions from many organizations, including Databricks, Cloudera, and Intel, as well as Mapr and IBM. And also we got contributions from freelancers as well as some early adapters, which make us very encouraged to progress on in this project. So here is some design overview about how we are doing this. So this is the goal we want to reach when we when we architecturing the project and when we do the design. So we don't want to to impact the existing Hive code path. So we like the things that work, the features should be continue work in with this inclusion of the new execution engine. And we want to also maximize reusing the existing code base. And also we like to minimize the future customization work. So in the future, if there are new features, you don't need to provide like 3 implementations, one for each execution engine. Therefore, we also envision that future maintenance costs with no. So if you if anyone develops a new feature in Hive, as long as it's above the backend execution layer, then it should be available in each of these alternatives. So here is a little bit of in Hive internals. So on the left, as you can see that it's a Hive client. That could be any client, JDBC client or Beeline. On the left is the Hive metastore, which provides the metadata access about your tables, your partitions, or your indexes, etc. So in the middle, that's the core of Hive, which is the Hive Server 2 services, so which doing the querying process, job submission, etc. So the Hive Server 2 works as follows. So the parser accepts a query, and which will parse it into a AST, that stands for abstract syntax tree. And there's a semantic analyzer, which further processes the AST into an operator tree. So after that, there's a task compiler, which compiles this operator tree into tasks that could be executed by the Hadoop client on the Hadoop clusters. So as you see in previous slides, I highlighted the task compiler, which is where we plug in our implementation for Spark. So this is the existing class hierarchy about the task compiler. On the top are all the abstract classes, which has 2 implementations currently. So a task compiler generates one or more tasks. So each task is described by a work. So the 2 implementations, one for each existing execution engine. That's MapRead for MapReduce and TAS for TAS, of course. So all we did for Spark is a new set of implementations. Spark compiler, which compiles or generates Spark task, and a Spark task is described by Spark work. So work is the metadata for a task. So in MapReduce work, so you usually have one map work and possibly a reduce work. So if it is map only, there's only one work. So one map work, there's no reduce work. Spark work, on the other hand, contains a graph of map works and reduce works. For a simple query on the left, as you can see that for this simple job, because it contains group by as well as order by, for MapReduce, it has two jobs to do this. First MR job have a map work, reduce work. The first job generates some output and write into disk, and the second job pick that up to further processing. So if this same query is executed by Spark, as you will see on the right side, there will be just one job. So that the job looks like just one map work followed by 2 reduce works. So Spark client is on the same level as the existing Hadoop client for MR and TAS. So Spark client talks to Spark cluster, and right now we support the cluster types. We support including pretty much everything like local, Spark local, standalone, Yarn cluster, and Yarn client. So I highlighted the Yarn cluster because that's a recommended setting. And Spark client is responsible for all the job submission, error reporting, monitoring, statistic collection, etc. So in the core of the Spark client is a Spark context. That's an object that's created from Spark. It have some problems, and it's heavy weighted and thread unsafe, and it's designed for a single application. Therefore, it doesn't work well in Hive Server 2 because Hive Server 2 supports multi-user sessions, and it doesn't scale, of course, with the user sessions. When you get more user sessions, if you have even there's no thread safety issue, then if you have multiple instances in your process, then your process probably won't be able to support that. At least it won't scale with that. So we have a solution called a remote Spark context, where Spark context is not is created outside and live outside of Hive Server 2, and in Yarn cluster mode, Spark context lives in the application master. So otherwise, Spark context will live in a separate process, so other than Hive Server 2. So in this diagram, I showed you in the Spark cluster, Yarn cluster mode, where you have multiple user sessions. Each session would have a Spark master, application master in the Yarn cluster, and the Spark remote Spark context lives in that application master. So therefore, you can have as many user sessions as you would. So a little bit of detail about data processing, and I will outline what's the difference between MapReduce and the Spark. For MapReduce, as you know that okay, good. So MapReduce, so the data is written is read by the MR framework, and the data is processed by map-side processing. And the output from map-side processing is further shuffled by MapReduce framework, and the shuffled data is further processed by reduce side processing. And reduce output is either written to a temp file and picked up by subsequent jobs, or is returned to the user. So very similarly, this is how the data get processed in the context of Spark. In Spark, we treat the table as RDD, Hadoop RDD, and we apply a function as that function wraps the Hive's map-side processing. It's the same map-side processing as MR, and then the output is shuffled by Spark's transformations, such as group by K or sort by K, etc. Then the shuffled data is further is applied by another wrapper function that wraps the MR's reduce side processing. In the end, the output is either returned to the client or being shuffled again for the next processing. So here's some internal details about how we represent the plan that is a Spark plan. Is the whatever we get from Hive, and this is whatever what is translated to in Spark, and this is just a internal representation. Here is just for information only. And So here's the advantages. So we can reuse, as you can see that we reuse the map side processing and the reducer side processing. So they essentially do the same transformation for your data. And we try to be agnostic to Spark's special transformations. As you know that Spark provides a lot of transformation, like it can do count, it can do join, to do code group. So we are trying to avoid those because a lot of Hive features are implemented in Hive's operator. So we are using Hive's operator to achieve all those functionalities. So we don't have to tie it with Spark. And also, we don't need to reinvent the wheels because these are already there. And also, existing features like authorization, window functions, UDFs can continue to work if you just use if you switch your execution engine to Spark. And also, this design also opens to future features. So for new features, as long as it's not within execution engine, then you will get the features no matter what execution engine you will use. So of course, we also have a lot of challenges during the process. So like challenges on both projects. Like in Spark, there are missing features or functional gaps, such as a concurrent data pipeline where a Spark job can only output one set of data output at a time. So this doesn't work well in Hive's multi-insert, where you output you process the same data, but further down in the pipeline, you process the data slightly differently, so that but you insert into your different target tables. So this Spark doesn't work well for that. Caching helps a little bit, but ideally we should have a better solution for that. And also the Spark context issue that's mentioned above. And there are some Spark is written in Scala, and of course it provides a Java API, which is sort of different, or sometimes even it's not complete in terms of what's available in Scala versus Java. And there are further down scheduling issues. I will talk a little bit more on that. That's about how to schedule the executors for different jobs. For Hive, of course, there are a lot of code, and there are different contributors working on in different areas. So there could be there are a lot of merging issues. There are also last, but it's also troublesome in terms of the libraries, because Spark may introduce the same libraries but of a different version. So we have several incidents about of the same library but different versions introduced in Hive. So for the scheduling issue, because as you see in previous diagram, each user session basically owns a Spark cluster, and a cluster is made of by a set of a number of executors. So, but there would be difference on the usage of the cluster, like the heavy users and like light users, or even for a single user, user can run big queries versus small queries. So you don't want to say, okay, all the executors get hold up by one user and other users have low resources to use, or if the user go out for a coffee, then he's still holding those executors. So the solution we have is the executors up and down based on the load. So current status, quick update. So all the functionality is implemented. We actually complete the first round of optimization, and we will do more optimization plus benchmarking, and also we will so that it's actually beta released in CDH back in February, and this work is also released in Hive, Apache Hive 1.1, and Hive 1.1 is actually included in CDH 5.4, which is coming soon, and with the full support for selected customers. But I encourage you all you to give it a try and let us know your feedback. So for further updates, please follow this Jira. So a few more words on the optimization. So we have done the join-related optimization, including like a bucket map join and skill join, etc. We also did split generation and grouping. And we enabled the CBO, cost-based optimization, and vectorization. And of course, there will be more to come, including like a table caching and dynamic partition pruning. So in short, this is a really a community-driven project, and it got a multiple organization support, and this provides the benefits of the two communities, two projects, and we believe that it will benefit a large user base. And also, I believe this project is have a solid foundation, and of course, it's also a fast-moving and evolving project. So with this, I'd like to introduce Ray, who is going to share the benchmarks that we have done with you. Ray?
Okay. Good afternoon, everybody. My name is Ray Li. I work at Intel, and I'm a Hive committer. It's a great pleasure to be here to co-present with Xuefu, and I will give you the benchmark part. The benchmark was done on a cluster of 8 physical nodes. Each node has 32 logical cores and 64 gigabyte memory connected by a 10 gigabit network. And here's the components used to set up the cluster. Hive was built from the Spark branch at a revision about half a month ago. We run the benchmark using TPC-DS for both 320 gigabyte and 4 terabyte datasets. We compare the performance of the 3 Hive engines, the MapReduce, TESS, and Spark. Basically, the engines all share the same configurations. Each node is allocated 32 cores and 48 gigabyte memory. We have vectorization enabled. We have CBO enabled. The threshold for map join is 600 megabyte for TESS and Spark. MapReduce has a smaller value because data size is decided differently. And here are some configurations specific to TESS and Spark. You can see Spark is deployed in young client mode. Each executor has 5 gigabyte heap size, as well as a 1 gigabyte off-heap memory, which means each container is allocated 6 gigabyte memory. And each executor can launch 4 tasks concurrently, adding up to 252 slots in total. And as to the collecting the results, we have we run each query 2 times, and we measure the second run. This is to get a stable performance for each execution engine, and besides, Spark has a big startup overhead because it waits for a number of executors to register before it launches any tasks for better scheduling. For some cases, we also measure have-on ties without dynamic partition pruning, because this optimization is yet to be implemented for Hive on Spark. I will talk more about this later. Here are the results for the 320 gigabyte dataset. Yeah, you can see Spark does a fairly good job. It's the fastest engine for quite a few queries. And for these 3 queries, TAS is the fastest engine because dynamic partition pruning helps to improve test performance. This optimization is used to prune partitions when tables are joined on the partitioned columns. It has a good chance to dramatically reduce the data to be scanned, so improves the overall performance. And we plan to implement this for Spark in the future. So for these 3 queries, we also compared the performance of Hive on TAS with the dynamic partition pruning disabled. So you can see it really helps a lot. And here are the results for the 4 terabyte dataset. And this is a chart with MapReduce excluded, so you can have a better view of the numbers. And again, TAS can use the DPP to improve its performance. And so we also compared TAS without dynamic partition pruning. And you can see on this larger data set, when the optimization is disabled, Spark is a little bit faster. So so Spark is faster on these queries. We have we also have the 3 primitive queries. You can see on the left side, which are intended to test for table scan, simple map join, and simple shuffle join, respectively. So Spark is faster for the table scan and simple map join, and most of the TBCDS queries we have picked. Okay, and TAS is faster on the common shuffle join, and some certain cases like query 84. So to conclude, Spark is close or even faster than TAS for many queries, like mentioned above, and dynamic partition pruning helps the TAS a lot on certain queries. Without that, Spark is a little bit faster or close to TAS. For some certain queries, Spark is slower, like common join and query 84. The reason is still under investigation. And we also found that on the bigger dataset, Spark seems to performs better. And we also expect that Spark will be even faster when the dynamic partition pruning is implemented. Okay, that's it. Thanks.
So if you have any questions, that's a good time to ask. Yes.
Have you considered benchmarking Presto as well? Or if not, I'm curious why.
So we haven't considered that because as you see that we haven't got a chance to even do a larger scale comparison. This is like 8 node, so it's our first benchmark. But I would expect that we will have a larger scale benchmark, and probably we will also include more competitors in that space. Yeah, thank you. Yes.
When I want to replace my old Hive executor, if I want to replace the Hive executor, the old MapReduce Hive executor, when I should choose a Hive with Spark and when I will choose Impala.
Oh, so your question is about like a performance with Hive on Spark compared to Impala.
To Impala, because Impala is also working with Metastore. So
Right, right. So I guess the answer to that is I think Hive on Spark or Hive in general is for a different use case as a Spark. So Hive is more like for SQL tool for batch processing, while Impala is more for like real-time data analytics. I I would imagine that Spark will be faster, but if for a small query, but in terms of data throughput, batching, I don't know, but I would think that for that, Hive would be a better choice. Yes, on the back.
I have a question about compatibility with Hive. How about UDFs, user-defined functions? Can it be used as in normal Hive mode, with MapReduce mode?
Right. So I don't expect that there will be any change on your UDF. You will do the same thing as you do for if the execution engine is MapReduce. It's fully supported.
Hi. Approximately in Spark 09, the SQL execution engine started living separately from Shark. Well, I know the reasons behind it, and is it time to merge them back since Hive evolved significantly? The latest serious evolvement is a cost-based optimizer, transaction support, etc. Or you still want to get divorced?
I'm not sure if I got your question correct. So, your question is about Shark. What's the difference between this and the Shark, or?
The difference between Shark and Spark execution engine, it was rewrote from scratch. The reason, the different roadmap for Spark and for Hive. My question is, are you still going to have a completely separate execution engine, or try to go back to Hive since Hive team is ready to embrace you?
Yes, I would imagine that the best bet would be use Hive on Spark. Because either Shark or or Spark SQL per se, they all have the problem of matching the features because it only take the front end, like the front parts of the Hive. It basically make a clone of Hive for certain components, but a lot of features in Hive is actually implemented in the operator layer. We mentioned there are operator trees, so to feature richness and to get the most updates, like the new features, all those other projects will have a hard time to match with Hive. So with Hive on Spark, so you got automatically all the features that you need from Hive, so nothing would change because of this new execution engine. So you will get Hive on Spark will keep improve with Spark, right? And this enhancement will be completely transparent to you, so you won't have to worry about that. So you will continue use what you get used to with Hive.
Hi.
Yes.
Working? Yeah. I had a question about your configuration. How many disks are in those Hadoop nodes?
We have 6 disks each node, but it's managed by the LVM. So I think we cannot do parallel disk I/Os. So yeah, it's just like I think it's just like serialized disk I/O. Yeah.
Okay, you said it's managed by LVM.
Yeah.
Okay, and is it a good idea?
Well, we also tried using multiple disks in our previous tests, and it does improve performance. But in this benchmark, we didn't get the servers that has that the better configuration.
So to add this, so this benchmark is like, to me, is a very babyish because it's like a 8 node and the disk or the cores are, is not that powerful. So this just give you a like over preview maybe, but we will provide a more like a benchmark which probably makes more sense or more representative in the new future. Yes.
I have a question about the deploying Spark cluster. What's the best option to deploy Spark? I know that there are standalone mode, yarn mode, and Mesos, but which is the best option and which is used in connection with Hive?
Sure. So the question was, what's the best deploy mode for your Spark cluster? So our recommended deployment mode is yarn cluster. As I mentioned, there are several other nodes, several other deploy modes like Mesos and standalone. So we don't support Mesos. And standalone, we won't recommend it. And of course, it has like a local cluster. These are more for like debug and testing. So the recommended mode is yarn cluster mode. This is just as you see from my answer to the scheduling, right? So the process which launched the Spark context is in the Spark in the application master, which is distributed in your cluster as well. So you won't burn your Hive server to node if you use other mode like yarn's client mode.
So if you run Spark on Amazon EC2, would you still recommend running it on top of a yarn cluster or not?
So, good question. I never tried on Amazon, but I imagine that it still should try the yarn cluster. But I can further check that. Yes.
You recommended to use yarn cluster mode, but how it works with Hive? Just because if I'm trying to run, for instance, Spark shell in yarn mode, it doesn't allow me. I can use Spark submit only. I need to submit completely jars to application master if I want to have a Spark cluster. If I want to use Hive or Spark shell, I need to use yarn client, I guess. Is it correct?
Well, yes, Spark Share works with the yarn client mode, but when you use a Spark Share, right, to submit a job, that's not a Hive job, right? So here we are talking about like run Hive on Spark with what kind of deployment we need. So what I'm saying is that yarn cluster is the mode that we recommend. But for your case, you may just your Spark Share is a different application. It can have a different deployment mode for your cluster. But it's still, right, you still have the same yarn resources manager, right? So it's still.
Yeah, the difference is where it's run. It's run on the client or run on application master.
Right.
And no application master knows that I've run executed the next Spark SQL.
Right, but your application would be different. Here the application is Hive on Spark. Your application is Spark Share, right? Which could have a different deploy mode. Yeah, thank you. All right, I guess that's it. Thank you very much for coming. And if you have any questions, catch us either here or in the community hangout or something. So email us. providing feedback. Thank you very much.